So your next type of multivibrator is called as your bistable multivibrator. Okay. So bistable multivibrator using 555 timer. So what is meant by bistable multivibrator? The name itself gives you the meaning. Bi means two. Okay. So it basically consists of two stable states. Okay. So we have seen already what is meant by a stable multivibrator and monostable multivibrator. A stable multivibrator does not have any stable state, whereas in monostable multivibrator we have one stable state. So in order to get one stable state, we have applied one trigger. So here in this case it has two stable states. So in order to obtain this two stable state, we are applying two triggers. Okay. So what will be your waveform? Suppose let us assume that initially the output is in the low state, okay, in the off state or your low state. Once it will be in this state permanently until and unless I apply a trigger. So when I apply a trigger here, the state changes from low to high, okay, and it will be permanently in this high state until and unless a second trigger is being applied. Okay, so only when I apply the second trigger, the state changes back to your low state. Again it will be in this low state permanently until and unless you are going to apply the next trigger. This repeats itself. So in order to change from one state to another, you have to apply a trigger. Okay. So this is how you will be getting the output of your bistable multivibrator. So basically your bistable multivibrator is also called by another name called as flip-flop or latch. Okay. So the meaning is that because it flips from one state and flops back to the other state. So basically it is also called by the name called flip-flop. Okay. So as we have seen before, this is your pin diagram where your 8 pin IC, first pin will be your ground, second trigger, third output, fourth reset, fifth control voltage, sixth pin will be your threshold, seventh pin will be your discharge pin, and the eighth pin will be your supply. Okay, and this is your pin configuration for your bistable multivibrator. So in the case of bistable multivibrator, what is the changes you have? So normally in the previous two cases, you will be connecting your 8th pin and 4th pin to your VCC. Okay. So in this case, in short, if you tell, the bistable multivibrator is being controlled by your trigger input, that is your second pin and your reset pin, second pin and your fourth pin. Okay. That is your reset pin. So 8th pin will be given to your supply, and your fourth pin and the second pin, that is your trigger pin and the reset pin, will be connected to your VCC through your both the resistor R1 and R2. This is your configuration. Okay. Seventh pin is not connected. Sixth pin will be given to your ground, and there are two switches. One is your switch S1 and the other is your switch S2, which will be connected to your trigger and your fourth pin respectively. So this will be here, you will be giving a short pulse, trigger pulse. Okay. So this is how, and as in the same case of the previous circuit, pin number 1 will be grounded and fifth pin will be connected to your capacitor and it will be grounded. That is for noise compensation. And the third pin will be your output pin. Okay. So this is your configuration of your bistable multivibrator. So in this case of bistable multivibrator, if you want to find out or if you want to explain the output, you will have to go for your functional block diagram. So as we have seen in the previous video, this is going to be a functional block diagram which will consist of again three same 5 kilo ohm resistor with two comparators. So if I take this as comparator 1 and comparator 2, the output of the comparators will be given as input to your SR flip-flop. Okay, and the output will be connected to your, which is nothing but your inverter. It is an inverted output. Output will be obtained through your third pin, and it is again connected to your that is your discharge pin as well as your fourth pin, that is your reset pin. So these are the important connections of your functional block diagram. This will be a reset pin. I have just configured as per that of your bistable multivibrator. As you can see, the fourth pin will be connected to your VCC through your resistor R1. So it's not R1, right? It's R2, and your second pin will be connected to your VCC through your resistor R1. So this is how your connection, and you have two switches correspondingly, S1 and S2 and S1. So this is how your configuration is. So suppose that we can assume that, let us go for the first condition, case 1. Okay, case 1, initially when you have your sixth pin is connected to the ground, right? So when you have the sixth pin connected to your ground, you have 0. The value will be 0. And what will be your upper threshold point and the lower triggering point? So here you have, with, as we have seen in the previous video, you can just go through it. So this is going to be your 2/3 VCC, and this is going to be your 1/3 VCC. Okay, so when your sixth pin, that is your threshold pin value, is connected to your ground, that is if it is 0, your 2/3 VCC is greater than 0, right? So what will be your inverting terminal is greater. When your inverting terminal is greater, what will be your output? Output of your comparator will be equal to 0. So negative is greater means your output will be 0. Similarly, we can see your second comparator. So in the case of second comparator, second pin is normally connected to your VCC. Okay, so now if this is your VCC, VCC is greater than 1/3 VCC. So VCC is connected to your negative potential. So in the second case also, second comparator also, your negative is greater than that of 1/3 VCC, because here you have your VCC supply voltage. If supply voltage is 5 volt or 10 volt, 10 will be greater than that of your 1/3 VCC. So here, since it is negative is greater, here also the output will be equal to 0. Output of the both the comparator will be 0. So you know that SR flip-flop, as we have seen before, if the condition is 0 0, it remains in the previous state. Okay, it remains Q. What will be your output? Qn plus 1 will be equal to Q1, previous state. So suppose let us initially assume that it is acting as a memory, right? Because your input is 0 0, your output Q will be equal to 0. When Q is equal to 0, what will happen to your Q bar? Q bar will be equal to complement 1. Now, what will be the output of the 555 timer? It will be given to the inverter. So output will be 1, Q bar is 1, so the output will be equal to low. So in the first case, you have assumed that it is in the memory state and your output is equal to 0. So if I can write here, in case 1, sixth pin will be grounded. The output of comparator 1 and comparator 2 will be equal to 0, right? And therefore the output will be equal to, output of 555 timer will be equal to, that is at the third pin will be equal to low, okay, or 0. Now let us go for your case 2. Case 2, now your state will change. So the output is equal to 0 in the first case, case 1. Now in the case 2, if I apply a negative trigger across this second input, okay, so I am applying a small trigger across your second input. So as soon as I apply a negative trigger, this value will go to negative. So now 1/3 VCC will be greater than that of your negative. So positive terminal will be greater. So what will happen to your next case? What will be your output? Output will change from 0 to 1. So S will be equal to 1. When S is equal to 1, Q will be equal to 1. The previous reset will be remaining in the same condition, 0. So now your Q will be equal to 1. When Q is equal to 1, Q bar will be equal to 0. Since this is a inverting buffer, right? Output will change from 0 to 1. The 555 timer output will be going to high state. So the meaning is that if I apply a trigger here, what will happen? The state changes from low to high. Okay. So this is how. So how will your circuit? This is how your, through the second pin, I'm going to apply your trigger. So this is your output. You will be getting it in Q. Let me repeat it once again. When I apply a small triggering pulse across your second pin, what will happen to your second pin? Second pin will go negative. Okay, so 1/3 VCC will be greater than this negative value. It is connected, 1/3 VCC is connected to positive terminal. Now positive terminal will be higher. So your comparator 2 will get the output, will shift the output from 0 to 1. Second case, when set is equal to 1, you will be having Q is equal to 1. Q bar will be equal to 0. The output of the 555 timer, which is an inverted buffer, will be equal to high. Okay, so in the case 2, what you are going to do, your comparator 2 output will be equal to 1 and your output of triple output at third pin will be equal to high. Okay, now you have to make a very important point here. The trigger is for a very small instant of time, very fraction, a small fraction of second. So once the trigger will get will go back to 0 after a small instant of time. Once it gets back to 0, the condition here, the comparator will go back to your initial state. It will go back to your 0. Once it turns to 0 again, both will be 0. S and R will be 0. So the output will be remaining in the previous state itself. So the output will remain in the previous state itself. So what will be your output of your comparator? Output of your comparator will be in the previous state itself. That is, it will be in the high state itself. So this is a very important point which you have to remember. So it goes back after the trigger pulse switch is open for after a fraction of second. When the switch is again open, what will happen? S and R will become 0 and your output Q will go back to your previous state itself. That is, it will be remaining in high itself. The output will be high permanently until and unless you are going for your next trigger. So let us take that as your case 3. So case 3, now if the state of high has to be changed, it will be permanently in the high state. Now if it has to be changed, now you have to go for your reset pin. Okay, so from the fourth pin, this reset pin, if I apply a small, if this switch S1 S2, right, S2, if the switch S2 is closed, if now I am applying a small reset signal. So in the case 3, when I apply a reset signal, what will happen? It resets. Reset will become 1, right? And S will become 0. So initially, before S is already equal to 0. So now when I apply a reset signal, R will be equal to 1. When R is equal to 1, what will happen to your Q? Q will be equal to 0. Okay, as per your table. So R is equal to 1, S is equal to 0, Q will be equal to 0. When S is equal to 1, R is equal to 0, Q will be equal to 1. So it resets the flip-flop. So when Q is equal to 0, what will happen to your Q bar? Q bar will be equal to 1. The output of the third pin will be equal to 0. So for the third condition, that is your third case, it switches from your state 1 to 0. So what will happen to this when I apply a reset signal? R will be equal to 1, S will remain in 0. So what will be your Q? Q will be equal to 0. Okay, when Q is equal to 0, Q bar will be equal to 1 and the output of the buffer at the third pin will be equal to 0. So it switches from your high state to your low state. Here also the switching action is only for a very fraction of second. So once the switch is opened, it will go back to your state that where your S and R will be equal to 0. Now when S and R is equal to 0, it remains in the same state itself, right? So what was your state? Now output is equal to 0. So your Q will be remaining in the same state, will be equal to 0. So Q bar will be equal to 1 and the output in the pin will be equal to 0. So permanently it will be in the stable state itself until and unless you are going to apply the next trigger. So in short, in the case of bistable multivibrator, if it has two stable state and if it has to change the state, you have to apply a trigger. Okay.